This section describes how to set up public and private subnets and Internet protocols. An Internet gateway serves two purposes. First, it provides a target in your VPC route tables for Internet routable traffic. It also performs network address translation, or NAT, for instances that have been assigned public IPv4 addresses. To enable access to or from the Internet for instances in a VPC subnet, first create an Internet gateway and attach it to your VPC. Then add a route to your subnet's route table that directs Internet-bound traffic to the Internet gateway. Confirm that each instance in your subnet has a globally unique IP address. And finally, confirm that your network ACL and security group rules allow the relevant traffic to flow to and from your instance. A network address translation, or NAT, gateway supports instances in a private subnet to connect to the Internet or other AWS services. But it prevents the Internet from initiating a connection with those instances. To create a NAT gateway, specify the public subnet in which the NAT gateway should reside. You must also specify an elastic IP address to associate with that NAT gateway. After you create a NAT gateway, you must update the route table that's associated with one or more of your private subnets to point Internet-bound traffic to the NAT gateway. Thus, instances in your private subnets can communicate with the Internet. All subnets consist of a contiguous range of IP addresses. These addresses should not overlap with other subnets in your VPC. Interfaces that are attached to EC2 instances in private subnets are not reachable from outside the parent VPC. However, by using an AWS managed NAT gateway, EC2 instances can make outbound requests, such as for patching, and the response from the external resource will be allowed back in. Private subnets are often used to host database instances that don't need to be accessed through the public Internet. And a NAT gateway must have an elastic IP address assigned to it. When external traffic needs to reach an interface such as an EC2 instance, the interface must have a public IP address assigned. Also, the subnet's route table must include an entry to the interface. With these two factors in place, the subnet will be determined a public subnet. IP addresses enable resources in your VPC to communicate with each other and with resources over the Internet. When you create a VPC, you assign a classless interdomain routing or CIDR block to it, which is a range of private addresses. After you create a VPC, you can't change that range in the VPC, so choose it carefully. Note that CIDR ranges of subnets shouldn't overlap. When you create a subnet, it requires its own CIDR block. For each CIDR block you specify, AWS reserves 5 IP addresses in that block. You can't use these 5 addresses. When you create a VPC, every instance in that VPC gets a private IP address automatically. You can also request a public IP address to be assigned when you create the instance by modifying the subnet's auto-assign public IP address properties. A public IP address is used to access the Internet. Public IP addresses are dynamic. If you stop or start your instance, a new public IP is assigned. An elastic IP address is a static public IP address designed for dynamic cloud computing. You can associate an elastic IP address with any instance or network interface for any VPC in your account. By using an elastic IP address, you can mask the failure of an instance or software by rapidly remapping the address to another instance in your account. Alternatively, you can specify the elastic IP address in a DNS record for your domain, so that your domain points to your instance. An elastic IP address comes from Amazon's pool of IPv4 addresses or a custom IP address pool that you have brought over to your AWS account. Additional costs might apply when you use elastic IP addresses, so it's important to release them when you no longer need them. An elastic network interface is a virtual network interface that you can attach or detach from an instance in a VPC. A network interface's attributes follow it when it's reattached to another instance. When you move a network interface from one instance to another, network traffic is redirected to the new instance. Each instance in your VPC has a default network interface, called the primary network interface, which can be assigned a private IPv4 address from your VPC's range. You can't detach a primary network interface from an instance, but you can create and attach an additional network interface to any instance in your VPC. A route table contains a set of rules called routes that direct network traffic from your subnet. Each route specifies the destination and the target. Destination is the CIDR block where you want the traffic to go. The target is the gateway, network interface, or connection that destination traffic is sent through. By default, every route table you create contains a local route for communication in the VPC. But you can customize route tables by adding routes. Each subnet should have its own route table, or it will use the main route table of the parent VPC. Here are the key takeaways for this section of the module. Public subnets are used when external traffic needs to reach an interface, such as an EC2 instance. Private subnets are often used to host database instances that don't need to be accessed through the public internet. And route tables determine where traffic is routed in your VPC. Thanks for watching. This section provides information about using security groups as part of securing your infrastructure. A security group acts as a virtual firewall for an instance, and it controls inbound and outbound traffic. Security groups act at the instance level, not the subnet level. Therefore, each instance is a subnet in your VPC can be assigned to a different set of security groups. At the most basic level, a security group is a way to filter traffic to your instances. Security groups have rules that control inbound and outbound traffic. When you create a security group, it doesn't have any inbound rules. Therefore, inbound traffic that originates from another host to your instance isn't permitted until you add inbound rules to security group. By default, a security group includes an outbound rule that allows all outbound traffic. You can remove the rule and add outbound rules that allow specific outbound traffic only. If your security group doesn't have any outbound rules, then outbound traffic that originates from your instance isn't allowed. Security groups are stateful, which means that state information is kept even after a request is processed. Thus, if you send a request from your instance, the response traffic for that request is allowed to flow in, regardless of inbound security group rules. Responses to allowed inbound traffic are allowed to flow out, regardless of outbound rules. All rules are evaluated before a decision is made to allow traffic. The tables on the slide indicate that inbound traffic is allowed from any network interface assigned to the same security group. All outbound traffic is allowed. Here are the key takeaways for this section of the module. A security group acts as a virtual firewall for an instance to control inbound and outbound traffic. Security groups are stateful, which means that state information is kept even after a request is processed. And finally, all rules are evaluated before a decision is made to allow traffic. Thanks for watching. This section provides information about using Network Access Control Lists, or ACLs, as part of securing your infrastructure. A network ACL is an optional layer of security for your VPC and acts as a firewall to control traffic in and out of one or more subnets. To add another layer of security to your VPC, you can set up network ACLs with rules that are similar to your security group rules. Each subnet in your VPC must be associated with a network ACL. If you don't explicitly associate a subnet with a network ACL, the subnet is automatically associated with the default network ACL. You can associate a network ACL with multiple subnets. However, a subnet can be associated with only one network ACL at a time. When you associate a network ACL with a subnet, the previous association is removed. A network ACL has separate inbound and outbound rules, and each rule can either allow or deny traffic. Network ACLs are stateless, which means that responses to inbound traffic are subject to the rules for outbound traffic and vice versa. Your VPC automatically comes with a modifiable default network ACL. By default, it allows all inbound and outbound IPv4 traffic, and if applicable, IPv6 traffic. The table shows a default network ACL for VPC that supports IPv4 only. You can create a custom network ACL and associate it with a subnet. By default, each custom network ACL denies all inbound and outbound traffic until you add rules. Rules are evaluated in number order before a decision is made to allow traffic, and each network ACL also includes a rule whose rule number is an asterisk. This rule ensures that if a packet doesn't match any of the other numbered rules, it's denied. You can't modify or remove this rule. Let's summarize the differences between security groups and network ACLs. First, security groups act at the instance level, but network ACLs act at the subnet level. Second, security groups support allow rules only, but network ACLs support both allow and deny rules. Next, security groups are stateful, but network ACLs are stateless. That means that security groups automatically allow return traffic, but network ACLs must explicitly allow return traffic. And for security groups, all rules are evaluated before the decision is made to allow traffic. For network ACLs, rules are evaluated in number order before the decision is made to allow traffic. Let's review the VPC security features that we've covered. Security groups act as virtual firewalls for your EC2 instances to control inbound and outbound traffic. Network ACLs provide an optional layer of security for your VPC. They act as firewalls to control traffic in and out of one or more subnets. Subnets make networks more efficient. Through subnetting, network traffic can travel a shorter distance without passing through unnecessary routers to reach its destination. And route tables control where network traffic is directed. Another feature of VPC is VPC flow logs. With this feature, you can capture information about the IP traffic going to and from network interfaces in your VPC. You can publish flow log data to Amazon CloudWatch Logs or Amazon Simple Storage Service, also called Amazon S3. After you create a flow log, you can retrieve and view its data in the chosen destination. You can create a flow log for VPC, subnet, or network interface. If you create a flow log for a subnet or VPC, each network interface in that subnet or VPC is monitored. Flow log data for a monitored network interface is recorded as flow log records, which are log events consisting of fields that describe the traffic flow. Here are the key takeaways for this section of the module. A network ACL is an optional layer of security for your VPC and acts as a firewall to control traffic at the subnet level. Each subnet in your VPC must be associated with a network ACL. Network ACLs are stateless, which means that responses to inbound traffic are subject to the rules for outbound traffic and vice versa. And finally, rules are evaluated in number order before a decision is made to allow traffic. Thanks for watching. This section provides information about using load balancers as part of securing your infrastructure. The Elastic Load Balancing, or ELB, service automatically distributes incoming application traffic across multiple targets, such as EC2 instances, containers, and IP addresses. You configure your load balancer to accept incoming traffic by specifying one or more listeners. A listener is a process that checks for connection requests. ELB scales your load balancing device as traffic to your applications changes over time and can scale to the vast majority of workloads automatically. This increases the availability and fault tolerance of your applications. You can add and remove instances from your load balancer as your needs change without disrupting the overall flow of requests to your application. ELB can handle the varying load of your application traffic in a single availability zone or across multiple availability zones. You can also configure health checks, which monitor the health of registered targets. With health checks in place, the load balancing device can send requests to only healthy targets. When the load balancer detects an unhealthy target, it stops routing traffic to that target. The load balancer resumes routing traffic to that target after detecting that the target is healthy again. ELB is integrated with other popular AWS services, such as Amazon EC2 Autoscaling, Amazon Elastic Container Service, or Amazon ECS, AWS CloudFormation, and AWS Certificate Manager, or ACM. ELB supports three types of load balancers: application, network, and classic. An application load balancer operates at the request level and routes traffic to targets such as EC2 instances, containers, IP addresses, and AWS Lambda functions based on the content of the request. It's ideal for advanced load balancing of HTTP and HTTPS traffic. This type of load balancer provides advanced request routing targeted at delivery of modern application architectures, including microservices and container-based applications. An application load balancer simplifies and improves the security of your application by ensuring that the latest SSL and TLS ciphers and protocols are used at all times. A network load balancer operates at the connection level and routes connections to targets such as EC2 instances, microservices, and containers within a VPC based on IP protocol data. It's ideal for load balancing both TCP and UDP traffic. This type of load balancer is capable of handling millions of requests per second while maintaining ultra-low latencies. A network load balancer is optimized to handle sudden and volatile traffic patterns while using a single static IP address per availability zone. A classic load balancer provides basic load balancing across multiple EC2 instances and operates at both the request level and connection level. A classic load balancer is intended for applications that are built within the EC2 classic network. How is data protected in ELB? First, a load balancer serves as the single point of contact for clients. The load balancer distributes incoming application traffic across multiple targets in the multiple availability zones. This increases the availability of your application. An application load balancer can sustain secure HTTPS communication and certificates for communications with clients. You can optionally terminate the SSL connection at the load balancer level so that you don't need to handle certificates in your own application. Second, if you enable server-side encryption with Amazon S3 managed encryption keys, also known as SSE S3, for your S3 bucket for ELB access logs, the ELB service automatically encrypts each access log file before storing in your bucket. ELB also decrypts the access log files when you access them. Each log file is encrypted with a unique key, which is itself encrypted with a key that's regularly rotated. And third, ELB simplifies the process of building secure web applications by terminating HTTPS and TLS traffic from clients at the load balancer. The load balancer performs the work of encrypting and decrypting the traffic instead of requiring each EC2 instance to handle the work for TLS termination. This diagram shows how load balancers work. This VPC has subnets in 2 availability zones. Each availability zone has a public subnet and multiple private subnets. Internet traffic goes from an internet gateway to each availability zone. A load balancer in each public subnet directs traffic to web servers in a private subnet in either availability zone. Traffic from the web servers goes to a load balancer, which directs the traffic to application servers in another private subnet in either availability zone. Traffic from the application servers goes to the primary database server in another private subnet in the first availability zone. And the primary database can communicate with the standby database server in a private subnet in the second availability zone. Here are the key takeaways for this section of the module. ELB automatically distributes incoming application traffic across multiple targets, such as EC2 instances, containers, IP addresses, and Lambda functions. ELB can handle the varying load of your application traffic in a single availability zone or across multiple availability zones. And finally, you can add and remove instances from your load balancer as your needs change without disrupting the overall flow of requests to your application. Thanks for watching. This section examines how all of these security features work together. This diagram shows how load balancing and VPC components work together. This VPC has 2 subnets, subnet A, which is a public subnet, and contains 2 EC2 instances. Traffic from each instance routes through a load balancer to a security group and then to a network ACL. Traffic then routes through a route table to an internet gateway. Subnet B, which is a private subnet, contains 2 EC2 instances. Traffic from each instance routes through a load balancer to a security group and then to a network ACL. Traffic then routes through a route table to a NAT gateway in subnet A, the public subnet. Let's look at some best practices to help protect your network. The first best practice is to apply controls for both inbound and outbound traffic. For a VPC, this includes using security groups, network ACLs, and subnets. Use subnets in multiple availability zones to separate layers of your application. And configure security groups and network ACLs to only allow necessary traffic inbound and outbound. Next, inspect and filter network traffic at the application level. Another best practice is to use threat intelligence and anomaly detection to automate protection mechanisms to provide a self-defending network. And finally, limit the exposure of the workload to the internet and internal networks by only allowing the minimum required access. Thanks for watching. Covers best practices for protecting your compute resources. Amazon Inspector is an automated security assessment service that helps improve the security and compliance of applications deployed on AWS. The service helps you identify security vulnerabilities and deviations from security best practices in applications, both before they are deployed and while they're running in a production environment. For example, the service can help you check for unintended network accessibility of your EC2 instances and for vulnerabilities on those instances. Amazon Inspector provides you the opportunity to define standards and best practices for your applications and validate adherence to these standards. This simplifies enforcement of your organization's security standards and best practices and helps to proactively manage security issues before they impact your production application. After performing an assessment, Amazon Inspector produces a detailed list of security findings prioritized by level of severity. You can review these findings directly or as part of detailed assessment reports, which are available through the AWS Management Console or API. Let's look at Amazon Inspector's security benefits. First, you can use it to automate responses to security issues. When you use Amazon EventBridge events with the Amazon Inspector, you can automate tasks to help you respond to security issues that Amazon Inspector findings review. Second, the service provides regular monitoring of your resources. Amazon Inspector helps to find security vulnerabilities in applications and departures from security best practices before your application is deployed and while it's running in production. This improves the overall security of your AWS-hosted applications. Third, you benefit from AWS security expertise. Amazon Inspector includes a knowledge base of rules charted to common security best practices and vulnerability definitions. AWS constantly updates the security best practices and rules. And finally, the service can help you integrate security into DevOps. Amazon Inspector is an API-bound service that analyzes network configurations in your AWS account. The service uses an optional agent for visibility into EC2 instances. The agent can help you to build Amazon Inspector assessments right into your existing DevOps process to empower both development and operations teams to make security assessments an essential part of the deployment process. Amazon Inspector uses the widely deployed AWS Systems Manager agent, also called SSM agent, to collect the software inventory and the configurations from your EC2 instances. Systems Manager gives you visibility and control of your infrastructure on AWS. Systems Manager provides a unified user interface so you can view operational data from multiple AWS services. The service includes capabilities that help you automate management tasks. You can collect system inventory, apply operating system patches, maintain up-to-date antivirus definitions, and configure operating systems and applications at scale. And Systems Manager helps keep your systems compliant with your defined configuration policies. Here are the key takeaways for this section of the module. Amazon Inspector is an automated security assessment service that helps improve the security and compliance of applications deployed on AWS. Systems Manager gives you visibility and control of your infrastructure on AWS. And finally, scan your compute resources regularly for vulnerabilities and patch them accordingly. You can automate this task by using AWS services such as Lambda and Systems Manager. Thanks for watching. It's now time to review the module and wrap up with the practice certification exam question. You should now be able to define the components of a VPC, recognize account boundaries, and describe AWS services that are available to protect your network and resources. Now let's look at a simple exam question. A system administrator created a single EC2 instance and set up network ACLs and the appropriate subnet routing. However, they want to provide an extra layer of security by applying a firewall to control access to and from the EC2 instance. Which action should the system administrator take? Option A, create a network ACL. Option B, configure a security group. Option C, update the subnet route tables. Or option D, set up a load balancer. Note the key requirements stated in the problem. The keywords to focus on here are applying a firewall and control access to and from the EC2 instances. Consider the answer choices and rule them out based on these key requirements. We'll pause a few seconds before discussing the correct answer. So how do these answer choices compare to the requirements? Well, a network ACL acts as a firewall to control inbound and outbound traffic, but it operates at the subnet level. So that's not going to meet the need. A security group acts as a virtual firewall for your EC2 instances to control inbound and outbound traffic. That could be the answer. A route table is used to control where network traffic is directed. It doesn't function as a firewall, so that's not going to meet the need. Finally, a load balancer automatically distributes incoming application traffic and scales resources to meet traffic demands. It doesn't function as a firewall, so that doesn't meet the need. Let's see what the correct answer is. The correct answer is B, configure a security group. That concludes this module. Thanks for watching.
Protecting data in your application module. This first section provides an introduction to the module. At the end of this module, you should be able to describe how to protect data at rest and in transit, identify Amazon Simple Storage Service or Amazon S3 protection features, and encrypt data in Amazon S3. You should also be able to differentiate between client-side encryption or CSE and server-side encryption or SSE, and identify AWS services that help protect your data. This module is broken into sections, each with its own video. Let's discuss how the concepts in this module are applicable to the bank business scenario. John was receptive to Maria's presentation and appears supportive of her plan to secure the bank's assets from outside attacks. However, Maria noticed that John still seemed unsure of the security capabilities inherent to AWS. John explained that at his previous employer, a disgruntled employee had accessed some inadequately secured user data inappropriately. This wasn't discovered until after the employee had left the company. This breach cost the company a large amount of money in fines and settlements. For John to be comfortable with migrating to the cloud, he needs to understand how user data would be protected in the cloud. For their next meeting, Maria wants to explain how they can secure user data that's stored in the cloud. This module covers two portions of the shared responsibility model. The first is client-side encryption and data integrity, including authentication. The second is server-side encryption for file system and data. The customer is responsible to secure these portions. Thanks for watching.